Hello and welcome back to the natural number game using Lean 4. Today we're going to continue off with the inequality world and tackle level 9, less than or equal to total. And level 9 states that given two natural numbers a and b, that a is less than or equal to b, or b is less than or equal to a. So let's think on how to prove this. One way to just start making progress here is with induction on b. We can induct on either variable. I think, we can induct on either variable. It's symmetric. So we'll have two cases: 0, successor b with our inductive hypothesis. Okay, let's solve the 0 case first. A less than or equal to 0, or 0 less than or equal to a. So we need to prove just one of them because our goal is an or. And we have, we have 0 less than or equal to. So that's just 0 is less than or equal to a, so we can use that. 0 less than or equal to a, so we have exact. So we can do or dot the right side 0 less than or equal to a. Yes. Cool. So that solves the case if it's 0. Okay, so now we're not dealing with 0. We're dealing with successor of b. And what do we do in this case? Yeah, this is where I got really stuck last video when I was trying to do this on my own, and I spent like 30 plus minutes and I couldn't figure it out. Well, let me kind of quickly say high level when I try this again on my own, what are some of my thoughts and findings and discovery were, and then that'll lead us to a solution together. So, okay, with our inductive hypothesis, we know that either a is less than or equal to b, or b is less than or equal to a. And from this, we need to get either a is less than or equal to b plus 1, or b plus 1 is less than or equal to a. Okay. So if the only thing we have is our inductive hypothesis. So we have to use our inductive hypothesis. Okay, and then with an or statement, the way it works is this kind of turns into either from the left side, prove this statement, or from the right side, prove this statement. So with a less than or equal to b, we need to pick one of these, left or right side, and prove them. And with b less than or equal to a, we have to pick one of these sides and prove them. Okay, the left case is a lot easier. A less than or equal to b, well, we just add 1 to b. And that's true by less than or equal to successor. If we have a less than equal to b, then we have a less than or equal to successor of b, and we proved that in the last episode. The harder case that was really confusing for me for the longest time was what to do with b less than or equal to a. My thinking was, okay, if we look at the left side, well, we can't really prove that because it's pointing the wrong way. But then with b less than or equal to a, it's also hard to prove the right side. Because and I think my key insight for when I was able to finally get unstuck is with b less than or equal to a, both of the either the left side or the right side is true depending on specific choices of b and a. So imagine that b equals a. Well, then let's say a is 3 and b is 3. Well, then 3 is less than or equal to 4. Okay. What if a is 5? Or what if a is 3 and b is 1? Then 2 is less than or equal to 3. So it actually really matters what the values of b and a are. So we can't just prove the left side or the right side from b less than or equal to a. We need to actually have another split somehow and prove left side in some cases and right side in some cases when b is less than or equal to a, and vice versa. Okay, so with that in mind, let's remember, oh yeah, so for this we can do or dot elimination. So we have a inductive hypothesis, and this leads into functions. And then the way I usually figure this out is like, okay, what's going on here? I can mouse over this. We see that we have a is less than or equals to b implies the whole thing. So we have a less than or equal to b is true, and we need to imply the rest of it. So we can do function a less than or equal to b, and then, sorry. Okay, and then similar here, we have function, but here we have b less than or equal to a, and we also need to prove the whole statement. Okay, so this one's pretty straightforward. We can just we actually don't even need to use, we're not in tactic mode, so we can just do a less than successor a b. Or dot left. Oh, a less than or equal to b. Cool. Nice, yeah. So that's, yeah, this is just saying a is less than or successor of b, given a less than or equal to b. I think I can even just do these, yeah, to have those be filled in automatically. Okay, that's the quote unquote easier case. Now let's figure out what the heck is going on here. Now let's start by entering tactic mode. Okay. So we have b is less than or equal to a. Okay, so here we can rewrite at b less than or equal to a. Okay, here we can turn our b less than or equal to a to having the explicit c, because these are definitionally equal. And then we can do like, what is it? Cases b less than or equal to a. Intro C hypothesis. Sorry. Okay. So H equals B plus C. C is a natural number. Okay, so here's where the cases come in. Either A is equal to B, and if A is equal to B, that means that C is equal. So cases C with 0 and successor of C. Okay. If B is 0, so you can rewrite add 0 at H. H. Cool. And then the left side is just true because of 1 add less than self. So we do the left side, and then this. We need to switch this. We write H add successor or 1. There's like something add is +1. 0 add successor equals add 1. And then add commutative. Oops. Add commutative. Nice. And then now this is in. This has it matched because it's formed in the same way. 1 plus, and this is also 1 plus. Okay. Nice. Now, okay. So quick recap of what we did so far. When in the case where b is less than or equal to a, we said, okay, well, that just means that a equals b plus c, and c can either be 0 or something plus a natural number. And if it's 0, well, then a equals b, and we prove the left side. Now, what if it's not 0? Okay, if it's not 0, we prove the left side. Now we're going to prove a less than successor b. Okay, the way we do this is okay, since this is b plus successor, we can move the successor around to b, and then apply the like this formula, and turn it back into it's b equals a plus c. We have a less than or equal to successor of b, or successor of b less than or equal to a. Okay. So now we're actually going to prove the right side, where successor of b is less than or equal to a, by having this be successor of b plus c. So rewrite okay, this set of add successor, add commutative, reverse add successor, reverse add commutative at h gets us that a equals successor of b plus c. And then we're going to want to prove the right side, so or dot that to get the right side. And then here, pretty much since we want to get the successor b, the way we like kind of, so what I would want to do that didn't work unfortunately is like if I do this, like let f or have f be defined as a successor b. Okay, so we have this f, which says that a less than or equal to successor of b is equivalent to well, these are backwards. A and successor of b. Okay, f says that successor of b less than or equal to a if and only if for some there is some c should a equals successor b plus c. What we have for h, a equals successor b plus c. Perfect. Now we should be able to just like rewrite f at h like, yeah, so tactic rewrite failed, did not find instance of the pattern in the target expression. There exists a c such that a equals successor of b plus c, but we almost have this. We just don't have this there exists c part, and then the way we solve that is we just say, okay, exists c. We specify, okay, our c exists. This is the tactic we used previously, even in the last section where, okay, now we want to get back to this. So we say, okay, there exists something that's c, and then that kind of exists turns our there exists in a goal state to something like that, and then we just try to ruffle at the end. So actually, I think if I do these in a different order, you can actually see what's going on. Can I do this? Exists C. Okay, never mind. We have to do it in this order. But yeah, that actually solves our proof because, well, we have our C. And then it just since does our ruffle at the end. After this exists C. I guess if we do this in this order, what if I comment you out? Okay, here we see what happens. Okay, so we apply this and then we go out to this situation. And then if I rewrite, we just have H exactly what we want our goal state to be. So we do this, we do this. We want A equals successor B plus C. And we have that after we do some rearranging of the formula. Whew. Then I think an exist tries a like ruffle at the end. We can put the explicit ruffle or exact H. I think there's like a or it tries trivial. I think trivial just searches the goal state. Oops. So I could do trivial. Trivial tries a few different goals, simple tactics to close a current goal. But there we have it. We proved that less than or equal to is total. So for all values a, b, in a natural number n, we either have a less than or equal to b or b less than or equal to a. Oof, and that was a pretty complicated proof that took me a long time to solve, and that was pretty hard, and did some stuff with ors and less than or equal to, big stuff with ors like or dot elimination for using ors in a hypothesis, and then or dot INL, or dot INR in using or in for like when we had it in our goal state. And you can see that here that in our b less than or equal to a, we actually had two cases where we need to prove the left side of the OR and the right side of the OR. So that's, I think, what tripped me up the first time I tried to solve this. Made it really, really hard for me, but we got there in the end. Yeah, thanks so much for watching. If you learned something or enjoyed, yeah, please leave a like and or a comment. It was a lot of fun making this video, and yeah, join us next time where we tackle more of the inequality world.